So now I'm going to give a little talk about environmental effects on the kinetics as represented in RNG. So in reality, the thermochemistry and the rate coefficient depend on more than just the identities of the reaction products and reactants and the temperature. So a lot of times you guys would see we have a K of T and a K equilibrium of T, and you think that might be the whole story about the rates in the thermo. But that's only true for ideal gases in this special limit I'm going to call the high pressure limit. And in every other case, the actual rate and thermo expressions are more complex than just your normal K of T. So in particular, for example, if you have your reaction happening in a solvent, then the solvent definitely changes the thermochemistry of all the solutes. And also the solvent has effects on the rate coefficient. So all the rate coefficients are changed, all the thermo is changed, and therefore if you want to specify what's going to happen in those reacting systems, you need to specify what the solvent is, right? So water is different than octanol. It really matters. Similarly, if your reactions are happening at an interface between two phases, for example, between platinum sheet and gas phase, then the interface has a pretty darn big effect on the reactions. And in fact, even in less drastic cases, like if you have two solvents next to each other, like water and octanol, at the interface, the reactions actually are affected by the fact that there's an interface. If you have electrochemical interface, where you have electric field present there too, like at an electrode, then the effects on the kinetics can really be drastic because of the voltage, right, through as well as the interface. And if you run chemistry in the gas in this room, and you take this gas outside when it's sunny, the chemistry is actually significantly different because the photons actually affect the chemistry. So these are all examples of how the environment can affect the chemistry beyond the temperature dependence that you guys are all familiar with, which is surely important. But then on top of that, there's all the other environmental effects. Now that means that if you report a simulation to somebody, you have to give them a kinetic model that specifies the environmental condition. And so if you're doing a solvent or an interface, you have to say, okay, what's the solvent? You have to say, what's the interface? You have to say, do I have photons or electric field present? And additionally, I'll tell you now, you have to tell the pressure. Now, there's a broad range of conditions where the pressure doesn't matter very much. So that's why in a lot of the models you've probably seen, there was no pressure there. It didn't show up. But actually, the pressure does matter in some cases. That's what I'm going to talk about mostly today. And in the cases where the pressure does matter, typically the composition of the bath gas also matters. It's not just the pure pressure itself, but it's actually what the collision partners are. And I'm going to come back to this whole topic in a lot of slides later. But first, I'll talk about these first couple things. So in RMG, we can represent solvent effects. So RMG lets you specify a solvent. I think you've already seen that in a few of the talks earlier. Like I think Matt had an example like that they showed. And what RMG does is it corrects the thermochemistry by adding an estimate of the delta G of solvation to the gas phase thermochemistry. So it just takes all the gas phase thermochemistry estimates, just like normal, and then it just adds in this extra factor. And exactly what the factor is depends on what your solvent is. So you tell it what the solvent is, and it just adds in a factor. And the way it's done normally is it uses a method called Abraham's method, which is a linear free energy relationship. That's like a correlation for solvation energies. And for the solutes, there's a group additivity method which creates the Abraham coefficients for the solutes. That's invented by a guy named Mintz, who I think actually worked with Abraham. And so we do a group additivity to get the solute properties. Then we combine them with the solvent following Abraham's recipe, and it gives you a delta G of solvation. Now, this is a highly limited method. It only works for solvents where somebody knows what the Abraham parameters are. which typically means solvents that Abraham studied. And I think there's 16 of them or something like that have good parameters available. So you have to stick to those 16 solvents. But it can estimate the properties of most solutes in those solvents. So Mrs. method gives you a good way to estimate, at least for all the neutral solutes, a pretty good way to estimate the delta G of solvation in those solvents. This procedure is really only good close to the conditions where somebody characterized the solvent, and typically that means room temperature. And so if you have a room temperature solvent that's on the list that Abraham studied, you're in good luck. And if you want to work far away from room temperature and Abraham didn't study it, well, too bad, because your RMG will not be able to estimate your solvation energy. We're working on trying to get more general ways to try to estimate the solvation energies. Yeah. A practical thing is there aren't really that many different kinds of solvents in the world that are widely used. So even if the solvent you want to use is not on the list that Abraham studied, you might be able to find a similar one. So for example, if you're doing a reaction in heptane, and Abraham has not studied heptane, but he did study octane, and you might say, well, my solvent's kind of like octane, so I'll use the parameters for octane. That actually works just fine. All right. Second solvent effect is diffusion limits. And RMG, when it's building a model in solution phase, imposes limitations on the how fast reactions can be, how much fast bimolecular reactions can be, actually trimolecular too, where it's because in the solvent, the rate at which these two guys can get close to each other is not quite as fast as it was in the gas phase. And so that hindrance is picked up by RMG. It's really based on the viscosity of the solvent. So for the 16 solvents that we have the Abraham premise for, I think we also have the viscosities for all of them. And so it estimates the diffusion limits from the solubilities and from the size of the solutes. And it has a method to estimate the size of the solutes just based on the formulas. Interestingly, and important to know, is that if a reaction is hindered in the forward direction, it's also hindered in the backward direction. So reactions that take a single molecule and break it apart into two fragments are also hindered by the solvent being present. That's sometimes called the cage effect, and it's quite important actually for some of the cases we do. Anyway, RMG handles that fine. Now is where you have to be careful about representations of models. RMG model internally is fine, it has the diffusion limit. If you dump the model out in Chemkin, Chemkin doesn't know about diffusion limits. And so I think what RMG does is it dumps out a Chemkin file which just totally ignores the diffusion limit. I'm not sure about this. We really should verify. If you dump it out and then read it into, for example, Matt's tool that he showed you yesterday, and you tell it it's in solvent effect, it'll put the diffusion limit back in, and it'll just be fine. However, if you just ran it in Chemkin that way, Chemkin would interpret it as a gas phase reaction, and it wouldn't know about the diffusion limit. Now, the field is at the moment of trying to correct this, and so you really have to know your solver and how it reads the files to know whether or not it's going to impose diffusion limits or not. And so this is completely, it's sort of you're at a cusp here where it's not so clear, it's easy to be confused. And if you pull a model out of the literature that was done in a solvent, it's possible that the person who made that model already corrected for the diffusion limit. And then if you corrected it again in Matt's software, you possibly might alter the predictions from what the original person got. So anyway, just beware. Yeah, this is not actually, turns out not to be a huge deal, but it's a small deal. Okay, a much more important thing is that RMG doesn't really know about many other solvent effects on rate coefficients. I think there's a very small handful of reactions that RMG does know about solvent effects on the rate coefficients, but most reactions, RMG has no idea. And if you ask it for the rate coefficient, it'll just give you the gas phase number. In particular, RMG knows extremely little about ions. And so if you ask it for the rate of ions in the gas phase, you'll get the wrong answer. If you ask it for the rate of ions in the solvent, you also get a different wrong answer. or maybe the same answer, which is wrong in both cases. So just beware. If you end up having ions, you better watch out what the numbers are that RMG is using. It may give you basically the neutral numbers. All right. Thermo. So the gas phase thermo is computed as enthalpies, heat capacities, entropies. There's a standard way to do this. Usually do it as NASA polynomials. If we add on the Abraham correction of the free energy of solvation, then you have to worry about, is the NASA polynomial being updated correctly? And also another aspect here is that the software that people use for liquid phase simulations, in that field they don't know about NASA because they're doing liquids, they're not doing rockets. And so they might not use NASA polynomials anyway. So you have to be aware. There's some kind of thermo issue here. And the free energy of solvation we're adding on is typically just a single number. It's a delta G. It's not broken up into delta H and delta S. And so its T dependence will be kind of screwy. And so exactly what will happen in the thermo files coming out, it's dumped out, particularly if they're dumped out to another program like Chemkin. I think it's not so clear. That would be correct. So really, this whole thing kind of works pretty well for isothermal problems. If you're doing them at near room temperature, you'll get a delta G that's about right, and all your equilibrium will be about right, and everything's okay. But once you get away from near isothermal, or you get away from room temperature, it's more iffy whether this thermo is going to be any good. And this is kind of an ongoing effort to try to fix this. So, if you're working on a problem that's sensitive to solvent effects, I would strongly suggest you talk with us. This part of RMG is still in development, and you can work with us to try to get it really working for what you need. There's some discussion about this online at that link there, and there's some examples there, and I think other publications we have. So it's not like it's at stage 0, but it's definitely at like sort of beta plus kind of level that it sort of semi-works a little bit, but needs some more loving care to make it really good. Reactions to interfaces are an even more primitive level, I would say. There's one publication, as far as I know, this one here, and so I'd say it's like alpha plus maybe, or beta minus version of software. There's a nice description of the research project, and this project is led by Professor West and Professor Goldsmith. And they're focusing on reactions on bare metal surfaces, so very important for catalysis. And if you're interested in this, I highly recommend you talk to Professor West or Professor Goldsmith. I'm sure they'd be happy to work with you and have good examples to demonstrate that their new software can work, and they have a lot of things to work on itself. All right, so I'm going to talk about mostly pressure, which I've worked a lot on. Maybe I know more about it than anybody, so you're right, the horse's mouth, and you'll see how well we really understand it by how well I can answer your questions. Okay, so if you have a system where the collision rate is not very fast, so say you had a low density gas, so the molecules float around in the gas for a long time between collisions. And if that was true, then you'd have a molecule, suppose you had an A molecule and a B molecule bumped into each other, make some amount of energy. They might react and make an adduct called C. But that C, when it's first formed, will still have all that energy. So A had some energy, B had some energy, they bombed together, they got some, maybe the reaction is exothermic, so they got some extra energy, and they're just sitting there bound together. And then eventually, there'll be some collisions with some other gas phase molecule, say some nitrogen comes along and bumps into this vibrating adduct, and it might take away some of the energy. And if it takes away a bunch of the energy, maybe this adduct will now be stable, which means that its energy will be below the barrier for further reaction, and the thing will just sit there. But if the gas pressure was too low, like in interstellar space, it might have to wait for a year before a molecule would come along and bump into it, and during that time, it would either react further to do something else, or it would react back to the reactant. And in fact, if you look out in interstellar space, you won't see very much of C at all, because this rate of stabilization of C from collisions is really tiny. Okay. Now, at atmospheric pressure, a lot of times stabilization is pretty fast. You have collisions more than once every nanosecond, so pretty many collisions. So actually, you stabilize a lot of things at atmospheric pressure. And if you're somewhere in between, like a lot of times we do laboratory experiments at a few torr pressure, that's about 10 to the minus 3 atmospheres. It's very convenient for a lot of experimental experiments to work there. But in that case, this rate is 1,000 times slower than it is atmospheric pressure, and so you can have more of these reactions that might go on or react back before they get collisionally stabilized. All right, and just like I said for the solvent effects affecting the forward and reverse rates by diffusion, the same thing happens here, that if I started with C, the rate at which it can react, say to go to A plus B, is going to be hindered by the fact it has to wait for enough collisions to bring its energy up and come over. And so both the forward and the reverse rates will be slowed down because it involves some energy exchange. Okay. Now this is only in the limit where energy exchange is slow. If you were in high pressure gas, you have a zillions of collisions, and basically the energy exchange is fast. And so this is basically instantly fast, and it's just equilibrated, and everything's Boltzmann, and then you just compute the forward and reverse. And in fact, that's what you did when you took Pchem, and they made you calculate transition state theory rates, is they just assumed everything was Boltzmann and used the Boltzmann formula, which is basically implicitly assuming that the thermalization was fast. All right. Now, you can make this mathematical by drawing little control volumes around every different energy state of C, and you can calculate a rate forming C, a rate stabilization of C, a rate C reacts this way, a rate C reacts back, and you can write down all the things that can happen to C, and you can say, I need to have a population balance. And from that population balance, conservation of excited state of C, I can write down what's the time evolution of that population of this state. And I can do it for every single state in the whole system. If I write them all down, I get a huge system of equations called the master equation. And that's the equation. If you solve it, will tell you what happens to all the energy states of all the species as function of time. Now, that's actually more detail than we want, because we just wanted C. We really didn't care about all this detail of exactly what all the energy states of C were. So we want a reduced representation of this. And we want to write down some rate coefficients that couple C and A and B without worrying about the energy states. And there's not very many of these Ks, so that's good for us. We don't have to calculate too many numbers. So we'll just calculate a few numbers. So, but we need a recipe or a procedure to go from this really detailed description to this really compact description of rate coefficients that we were using. And now we expect our rate coefficients are going to depend on the pressure because we know that this part of the rate depends a lot on the pressure. The collision, how many collisions you have depends on how much stuff you have. All right. So it turns out that unimolecular reactions are often pressure dependent in the gas phase. There's a nice link here with some introductory material about that. And just fundamentally, the issue is I need collisions to add or remove the energy from a unimolecular species, like to add energy to a molecule to get enough energy to react, or vice versa. If I'm going to form a unimolecular species, I have to be able to take away energy to stabilize it. The thermal relaxation time might be sometimes longer than the chemical reaction time at lower pressures, and so then you really see the manifestations of this problem. Now, a consequence is that the energy distribution of all the species will no longer be Boltzmann, and so we don't have a clear temperature, and so this causes like many headaches in trying to keep track of things. This temperature is like a great simplification of our lives, so we have to worry about that. All right, so if I start say from A plus B, and they react, and I'm at very high pressure, basically what happens is A plus B react, they form a highly energized C, but I have so many collisions that basically what happens is 100% of the C gets stabilized as C. So even though I formed it energized, I really don't have to worry about the fact that this stuff might react further because the collisions are happening so fast at high pressure that basically just stabilizes down. So in this limit, I can forget about this, and I just write my old-fashioned favorite Chemkin type style things, A plus B goes to C, and then I can say, okay, well maybe the C stays here for a while, and then it comes back up and goes over the barrier, And so I have C goes to D, and the same thing can happen with D. You can go to E plus F. And so I end up with 3 rate coefficients for these 3 reactions. That's all I got. And each of them is just a function of temperature, if I'm in this high pressure limit. And typically they're approximately Arrhenius, and everything's simple. So I'm super happy, and everything's great and easy in the high pressure limit. But if I reduce the pressure, I get some more complicated situation where maybe a third of the C's relax, but 2/3 of them go on and relax to form energized D's. And then the D's, maybe a third of those guys relax, but 2/3 of them go on to form E plus F. And then if I'm going to try to write it, well, I could write down the reactions I had before. A plus B goes to C, C goes to D, D goes to E plus F. But I have to write 3 additional reactions. A plus D might go directly to D, like this. Or C might go to E plus F, like that. Or A plus B might go directly to E plus F all the way through, and never form C and D at all. And so now I have 6 rate coefficients instead of 3. And all these rate coefficients would change when I change the pressure, because they're all dependent on exactly the rate of how much of the stuff's being stabilized. So now I have rate coefficients that are non-Arrhenius, they depend on temperature and pressure, and there's 6 of them instead of 3 of them. And so this is way more complicated than before. Now this really causes a lot of problems for RMG, because in the high pressure limit, we would just follow the individual steps. So A plus B reacts and makes C. RMG knows about that. It puts it in, no trouble. We talked about that before. But now, in low pressure, it might turn out that you're low enough pressure, A plus B going to E plus F might actually be the only important process. So pressure is very low, like interstellar space. I don't stabilize anything. And all I do is just react straight across. So I'd like to show when I'm simulating a reaction at high vacuum, I wanted just to say A plus B goes to E plus F. But RMG does not know that A plus B can go to E plus F, because RMG only has a reaction template that goes from A plus B to C. Then it has a separate template that goes from C to D, and has another template that goes from D to E plus F. And somehow we have to tie those 3 templates together to get the whole A plus B goes to E plus F. So the way it does it, when you turn PDEP on, is one of the options in the beginning of your RMG job, you expand the network using these species C star and D star, these kind of transient pseudo-species, and it grows the network this way, and it makes C star, and then C and D star can be formed from that, and so on. And it grows the network involving these excited states. But in the end model, I don't want the excited states to appear, because those are just transient intermediates, quasi-steady state species, so I want to remove them. So I put them in while I'm building the model, but then in the final model, I'm going to try to make sure that they're all gone. So let's see how we do that. And also, when I put in my final case, I want to get the overall case, say from A plus B to E plus F, that's going to depend on temperature and pressure. I want to get the whole thing correct. I'm not going to have the single rate coefficient from the rate rules as before. Okay, so let's get started. A plus B, RMG reacts A plus B. It says, oh, these can make C, but RMG recognizes I'm in a low pressure gas phase, so therefore C is actually going to be C star because it's going to be formed energized species. RMG knows that all energized species can get relaxed, so it would put this in, and it would say, okay, my initial core was A plus B went to C star, and the C star can get relaxed, and then RMG will do exploration of all the other unimolecular reactions of C, and find that one of them, for example, is C star can go to form D. So at this moment, RMG has started a miniature core and edge network just about this one reaction, similar to the huge network we have for the whole model. Now it's formed a little one on the edge. I meant to draw a slide picture of this. All right, draw it here. So here we have the core. It has many species in A and B and W and X and Y, all different species in there, also has reactions between them. And A and B, we found out we can make C, but it identifies that C is a warning, C is an energized species, so it makes another little miniature network here, like that. And it keeps track of this little tiny core and edge model, separately called the PDEP network for this reaction. And there might be other ones. For example, X plus Y might be able to react and make Q star, and they'll have their own little core and their own little edge of that PDEP network. And so RMGs do the bookkeeping to keep track of the overall core and then these little sub-networks for each different PDEP. Now, at the moment when I calculated this rate, using the high pressure limit rate coefficient from the rate rules, I calculated the formation of C was really high. So I want to add C to the RMG model. However, I'm warned from what happened before that the C is energized, and if the pressure is low, this might be really slow, and maybe the C star would just go right back to A plus B. So maybe I'm really wildly overestimating what the real rate when A plus B goes to C is. So I don't know. So I just build this network like this, and now I need to make an estimate of what can happen. So we need to have an edge flux to test if I need to put D in there. So I've listed the D's on the edge of this little PDEP network, but I don't know how fast it's formed. I have to figure out how fast. So let's think how to do it. Here to help you keep track of this, I wrote this as a double arrow. In the end, RMG is going to say A plus B goes to D as a reaction. But at this moment, it's just saying there's some chemically activated path where A plus B goes to D through some of these transient species. And I need to know this rate coefficient if I'm going to be able to calculate this flux of how fast D is formed. However, I don't know it. All I know in the RMG database are high pressure limit rate coefficients. I don't know these pressure dependent ones. So I had to figure out what this number is. If I can evaluate this number, I know the concentration of A, I know the concentration of B, and then I can estimate this thing. So I have to make an estimate of that rate coefficient. However, in order to compute that, I actually have to know the whole network in order to write down the master equation of all those balance equations in order to actually solve and figure out the K. But I don't have the whole network yet. I've only started to explore. I only have a partial network. So what RMG tries to do is build an overestimate of the rate coefficient K. And if I use an overestimate of the K, and I use these real concentrations, and this whole number still turns out to be tiny, then I can forget about D. And then it'll save me a lot of time. So I try to make an overestimate. So how do I make the overestimate? Is what I do is I just say, well, let's just solve it as if what I see is all that can happen. And then I don't make D star, I just assume this is D and it's stable. This is like an irreversible sink, sucking the flux through, and that's going to make the rate an overestimate by having that as irreversible sink. So I solve this little network, A plus B to C star with C, with M, and D. And that's going to, the solution of that will give me an overestimate of the effective rate from A plus B to D. And then I can use that in my next slide to evaluate an estimate of the flux of formation of D. And if that number is small enough that I know I can safely ignore D, otherwise I can't, and I have to keep worrying what to do. So suppose I do the evaluation, and with that overestimated value of K, D is still important. Then I have to put D star in explicitly and figure out what D star can do, just like I did with C star. And I grow the core of this PDEP network, and I add in that D star can be stabilized, and I add in other reactions to D star, for example. It might fall apart to D plus F. And now I can solve this PDEP network to give estimates of A plus B goes to D, a better estimate for that, and an estimate for A plus B goes to E plus F. And actually I'll get better numbers for going to C as well by doing this. And then I solve this one. And I just keep iterating the same procedure to grow and grow and grow the PDEP network until there aren't any more stuff on the edge that are fast enough to be important. So I keep evaluating those guys. Eventually I can print them all out and say they're all negligible, and I'm done. I have a complete network, I just solve it, that's my rates. All right, now how do we do it in detail? Well, what we know are the high pressure limit rate coefficients from the Boltzmann model, the Arrhenius parameters that we have in our database where we can estimate, where we calculate quantum chemistry. So we know a lot of K of T's, and we want to turn them into K of T and P's. We have the partial PDEP network. So we have all these different bits. And after we run along and we decide something's important, we can delete the excited state version of it, and we just put it in as a regular species. And we found all the species. I'm going to actually tell you in a second how we actually do the computation, but let's just talk about notation for a second. So a lot of the models you've seen in your life have reactions written this way. A plus B react to make E plus F. In Chemkin notation and Cantera notation, implicitly this means these are high pressure limit rates, and typically they're near Arrhenius. And that's the typical reactions you've always dealt with in your life. However, if you're at low enough pressures, you get ones that have some pressure dependence in them. And the notation for this is you put a parentheses plus M, parentheses, in the file, in both the reactant and the product. And what that means is use this rate law. The rate of this reaction is a K of T and P times the concentration of A times the concentration of B. You'll also see another notation, A plus B plus M equals E plus F plus M. In this one, this is appropriate in the extreme low pressure limit, so in interstellar space. And there, the rate law is going back to just K of T, just like it was here, times concentration of A times concentration of B, and then also concentration of M is now a thermomolecular reaction. So very low pressure limit reactions will be written this way. Normal high pressure limit reactions will be written this way. And these PDEP ones that we're worrying about right now are written with this funny parentheses notation. All right. So if you look at the big mechanism, you'll typically find all three of these formats. That's what it means. Before I tell you how to actually do the computations, I'm going to ask, when do I need to worry about it? You can see already this is getting kind of complicated. It definitely makes RMG take a lot longer because it has to explore all these PDEP networks as well as doing its normal job. And so you might prefer to stay in the pressure independent limit where you just don't have to worry about it. You don't tell RMG any pressure. You just click no PDEP off in the RMG input, and boom, everything runs fine. But then the question is that accurate? When is it important to do it? And this is an evaluation of that was done in this paper. And if you're interested in this question, I highly recommend you read this paper. And this gives a way to estimate how different the PDEP rate will be from the high pressure limit rate. And I think here this line is where the two rates differ by a factor of 2. So the PDEP is like more than a 50% correction. And at high pressures, then you're in the high pressure limit, and also at low temperatures. So the lower the temperature is, the higher the pressure is, the safer you are to just use the high pressure limit and PDEP off. And at low pressures and high temperatures, then you really have to worry about the pressure dependence. So those of you who have the misfortune to work in combustion problems, you're going to be down here all the time. And those of you who are working in atmospheric chemistry, a lot of times you'll be in the pressure independent limit, you don't have to worry about it. Rule of thumb, in 1 atmosphere, if you're below about 800 Kelvin, you usually can get away with not worrying about PDEP. So if you're down that regime, most of the time, for most reactions, you're okay. And if you're above 1200 K, you definitely have to be worried about PDEP because almost all the reactions are going to be pressure dependent significantly. All right. It depends on the pressure, it depends on the temperature, it depends a little bit on the exothermicity, the well depth, the exothermicity of the reactions, and it also depends on the size of the molecules. But the biggest effect actually is the temperature. So you can see that doubling the temperature, or from like 700 to 1500, really drastically moves these lines. And so a factor of 2 in temperature is worth about as much as 4 orders of magnitude in pressure. So although we talk about this as a low pressure effect, to a lot of extent, it's really a high temperature effect. The high temperatures, you really have to worry about it. You might say, well, why is that? And the way to see it is that if you come in at higher temperature, A and B will have more energy. So instead of being in this state, you'll be in this state. That means that when you get to C star, the difference between this state and this state, and these don't look that different in energy, But the rates of, for example, the reaction back, this one is like close to the threshold, this one is way above the threshold. The rates can be many, many orders of magnitude different. So a small change in the energy of the inlets has a gigantic effect on whether what this rate is. And this rate is the very sensitive thing. This is changing rapidly. This collisional stabilization is more or less independent of temperature, and it's basically just the pressure, and it's kind of linear in the pressure. This thing has like some very high power dependence on the energy. So the higher the energy is of the inlets, the more you need to worry about the stabilization effect. If you don't have it, you're doing all your reactions will be way up here somewhere, way, way, way above all the barriers, and all the reaction rates are super fast. All right, some history about this. So this method of building up these little PDEP networks was invented by a student named David Matthew of mine, actually my very first student. And he implemented it initially into a program called NetGen that was invented by Linda Broadbelt, who's now a professor at Northwestern, when she was a graduate student. That research was sponsored in part by Exxon, and because of that, Exxon got a copy of the code, and then David modified that code because they were funding us at the time, and made this program called XMG PDEP, which is NetGen with the PDEP networks exploration. This is a long time ago. It was before RMG was invented. Then RMG was invented a few years after this. We couldn't get rights to the Exxon-controlled code, and so we had to write our own code to get away from the intellectual property problems. And we did not have the PDEP implemented. But the algorithm was laid out. So these papers by David Matthews' thesis, a paper with Brenda of Exxon, and this is a nice J. Fiskin paper too. And also David was involved with Brian Wong in the development of this assessment of when do you have to have pressure dependence or not, the paper I just mentioned. Then, how long later? 6 years later, 7 years later, another student came along named Josh Allen, and he implemented Matthew's algorithm into RMG Java, and then he wrote the original version of RMG Pi, which is the code you're using now. By the way, Professor West, who was then a postdoc here, and there were some other students, Kanigawa and Goldsmith was a postdoc, was a grad student here, I think, at that time. Those guys like all huddled away and decided to do RMG Pi as a skunk works, not telling me about it for a while. There's no way I would have approved spending that much time doing skunk work with it. But they did. And in the RMG Pi version, they souped up the algorithm of Matthews and made it better. And that's the algorithm basically that you have now today. At that time, there was another program called Cantherm, which was a standalone program just to compute the pressure-dependent rate coefficients before they actually put it all into RMG. The way it's done in RMG Pi and the way it's done in Cantherm were very similar because we're by the same author, basically, Josh Allen. There was another code called Cantherm, which is confusing, by a guy named Sandeep Sharma. So some papers reference Cantherm and they mean one code and some and others because they use the same name. I don't know why. Since all that Cantherm stuff has basically been incorporated into a new code called Arcane, which has the great benefit of having a different name. I think maybe somebody's reading. All right, if you want to read about this PDEP in RMG as you have it now, Josh Allen's PhD thesis has a chapter about it, and there's a very good paper in PhysChem and ChemPhys by Josh Allen, Goldsmith, and me. It's all about the implementation and testing and comparison to other codes for doing this kind of thing. There's some discussion in the online documentation for RMG about this. All right. I guess maybe, well, are we guys talking about Arcane? Yeah.
We mentioned that.
Okay. A lot of the capability that's in RMG for pressure dependence has also been basically written into a standalone program called Arcane, which, much better than the old Cantherm, has the ability to actually do the network expansion and discover, to grow the PDEP subnetworks itself. So if you don't want to do this inside RMG, you have the option now to do it on a standalone program. And in some cases, that could be very beneficial for you. Instead of, because you do with RMG, you get everything else going on in RMG, and many other things can confuse you. That you just focus on what you want to do with Arcane. And the Arcane, well, you'll see in a minute, the way RMG does pressure dependence has a lot of approximations to make it fast and kind of robust. If you do it in Arcane, you can do things better, because the idea is that the human would be helping Arcane along just for the one reaction system. And so you would put more effort into it. It's like you assume that you care more about this reaction. If you don't care about it, just run RMG, it'll give you some number. If you care about it, you want to get the right number, then you run it with Arcane, you worry about all the details. All right. Now, I mentioned this problem that the master equation gives you equations for the population of every energy state of every species separately. And they'll all have different time dependencies. And so really, they're all being treated as different species. And in fact, experimentally, sometimes this is seen. So for example, if you have a laser that can see carbon monoxide in its V equals 2 state, you can do experiments and you can see that the time dependence of that signal is different than carbon monoxide in V equals 0. So there are cases where this is known experimentally that the different energy levels react differently. But this is usually way more detailed than we care about. They don't react that differently. And if you think the amount of effort you have to do to get rate coefficients for every vibrational state of every molecule, it's just like give you a headache. I mean, we have enough trouble getting one rate coefficient for the molecule. Trying to get one for every different vibrational state would be impossible. So we typically don't want what the master equations is doing for us. It's giving us way more than we want, and we even don't have a way to handle it. So we have to figure out how to somehow turn the master equation into these rate coefficients, K of Tp, that we're going to put into this model, right? We're going to write down a chemkin file, and we're going to write A plus B, parentheses plus M, E plus F, parentheses plus M. And then the chemkin file wants us to write numbers that are the parameters K for K of Tp. And if we do it, it'll put it into the ODE system and solve the reactant flow problem with the pressure dependence all correct. If we can write that K of Tp in there. But this problem is not trivial of how to go from the master equations down to the K of Tps. And because of that, historically, people have developed different methods. And each of the different methods gives you a different rate coefficient, K of Tp. So this is super annoying and causes a lot of people criticizing each other in the literature. Because for the exact same problem, even if they would get exactly the same master equation solution, people would infer that it implies a different K of Tp. And there's 3 methods for doing this computation implemented in RMG. One is called the Modified Strong Collision Approximation, MSC. And if you read the Allen paper in this thesis, that's basically what he focuses on most. Another method is called the Chemically Significant Eigenvalues method. This method was actually invented by a guy named Whittam, who was a professor at Cornell a long time ago. But then, for some reason, the people doing gas phase never read Whittam's papers because he always published about liquid phase. And so they didn't know about it. And Whittam wasn't good as a publicist, and so nobody ever cited his paper. So his paper was sitting there unread for a really long time. And then it was reinvented independently by Klippenstein and Miller, who then, as they were writing their paper and trying to do the citation search, discovered that Whittam actually had already thought of the same idea earlier. And then Georgievsky more or less worked for Klippenstein and did some more improvements on it and wrote some of the software that implements this. So this method is called the Chemically Significant Eigenvalues method, CSE. And then independently, another guy, same last name as me, he's Green, but it's different Green, wrote another method called Reservoir States method about the same time. So there were 3 methods in RMG. There's probably there's other methods actually in the literature. I've seen several other ones too. So those 3 are in there. Now these 3 methods can all be written mathematically in the same formulation, and they all depend on some certain vectors, and they differ in what values they give those vectors. So this is pretty, if you want to think intellectually about what we're doing here, this is very important, and you might want to read this section here. And some of this is discussed in the Allen paper. Okay, so the modified strong collision approximation, this is the one you're actually going to use the most if you're using RMG. It has some really simple assumptions. One assumption is that if you have a C star, all you need is a single collision to knock it all the way down to stabilize C. So this is kind of, I think, the Lindemann model. Everybody remember Lindemann model? Lindemann-Hinchelwood, maybe? A long time ago? So that's the model that those guys wrote originally. So it's called strong collisions. A collision so strong it can just take away all the energy and cool the molecule down. Not really very physical, because the collisions can't really absorb that much energy in a single collision. But a few collisions can take all the energy. So it's within an order of magnitude to be right. It has a huge advantage mathematically and in the formulation of the problem, because if you say that all you have is C star going all the way down to C, I don't need to worry about C star going to different C stars. I don't have to worry about all those intermediate energy states, because they're just totally constant. I just jumped over them with my magic strong collision, jumped over the top. So this is a great simplification. And it basically implicitly removes all the states that have energies less than the barrier height from the problem, because they never get connected. So you form the state up high, it jumps all the way down to the bottom, and it never hits those intermediate states, and so you don't need them. So it's like the express train. The energy goes right down past all those energy levels, never stops. You can just ignore them. Those towns are dead. The train doesn't stop, so too bad. Just get through them. All right. But that's great for you from the point of view of modeling, because you don't have to know anything about those states. Who cares? We're not going to stop there, so we don't care about them. And then it says, make a quasi-steady state approximation on the excited states. Now, that's probably what you would have done anyway. So that seems very reasonable, because those states are just transient, highly energized molecules. They're not going to live very long. And the effect of this whole thing is to take the master equation, which was a very large system of coupled differential equations, to be a set of a smaller number of simple linear algebra problems. And you can solve each of them like snap. And so it's super easy. Okay, so does this work? So one thing to let you know, this is a pretty rough approximation. Okay, we made a couple of physical approximations, and they're not really that great. And we've quantified this, and the errors, you get typically errors about a factor of 3 in a lot of the minor channels. So the major channels usually pretty close, and the minor channels less reliable, and factor 3 is not unusual at all to get that kind of error. However, this is super fast, and it turns out to be very robust. So almost every system in the world, you run it with this, you'll always get a number. It's always something sensible. It might be off by factor 3, maybe in a factor of 10. It's not going to be off by factor of 1,000,000. It's definitely not going to be off by Avogadro's number. It's definitely somewhere in the ballpark of reality. And this is very, very important for RMG, because we're going to estimate typically 100,000 or 1,000,000 reactions. And at low pressures and high temperatures, almost all of them are going to be pressure dependent. And so if you have to estimate 1,000,000 numbers, and you have a failure rate, say even in 1% of the cases, that's 10,000 failures. That's going to be a lot of problems for you to track down. So you really want robust. So robust is really, really important for RMG. And fast is good too, because you can do 1,000,000 of anything. If it's slow, that's bad, because it's going to take a really long time to do it 1,000,000 times. So these are really good things for RMG. So this is what we recommend you use. And also, I'll talk a little in a minute, there's other reasons why the RMG rate coefficients as a function of pressure are not going to be that great. They're not super accurate. The whole thing is not really intended to be super accurate. So because you have a lot of inaccuracy already, you get an extra factor of 3 on the accuracy. Well, who cares? I'm already off by factor of 5, so now I'm off by factor of 15. But it could be the other direction. Maybe I get better. It could be factor 1.5 instead of 3. Yeah, so you really don't know. So if your error bar is already pretty big, you don't really care that much. So that's the theory about this method. Now the alternative approach is like, you know, I'm a professional chemical kineticist. When I tell somebody a rate coefficient, it really should be the true number. Okay, so if you get that view, then why would you make stupid approximations like I just did in the previous slide? I should really do it right. And so in order to do it, what Witham and then Klippenstein and Miller discovered was that if you assume separation of timescales between chemical reactions and energy redistribution, then and you assume that the chemistry is the slow thing, the chemistry is slower than the energy distribution, then you can actually do some clever linear algebra, making that, relying on that approximation, or that assumption. And you can directly relate the eigenvectors and eigenvalues of the master equation to give you an expression for the real kx. So that's pretty cool. That's what Witham actually discovered. It's pretty amazing, actually. So what's the pros of this? If this assumption is valid, that you have a separation of timescales, this turns out that this is a very, very accurate method and definitely the best approach. So why don't we do it all the time? Okay, one reason is you have to solve the whole coupled large matrix eigenvalue master equation problem every time. And you have to compute some of the eigenvectors, which are also really big. And really big, like 100,000 or 1 million entries in the vector. So it's quite big. It's like a million by million kind of matrix kind of size. So this is kind of slow. So one issue is just CPU time. If you have to do 1 million reactions, you don't want to do them all this way. Now, if you're only doing 1,000 reactions, then you might want to do it this way. Another problem is that the eigensolvers that solve these eigenvalue problems have problems if the matrix is very stiff. And the consequence of this is that if you run this for a lot of cases at low temperature, you'll get non-physical rates. Not just that it'll fail and say, sorry, I can't calculate. It'll actually calculate it and just give you a wrong answer. And in fact, it might give you like a negative rate coefficient. It gives a lot of really crazy stuff because it's just numerical baloney. So this is quite alarming for robustness point of view because you don't know whether you can trust the rate coefficient you got. And at high T, some of the reactions get very fast. And so the reactions really are faster than the collisions physically. So this assumption is wrong. So therefore it fails too. So this method works really well at moderate temperatures where it's the best method, but it physically is incorrect at high temperature and numerically has tons of problems at low temperature. And so there's like a little range of conditions where it works pretty well. Now, the high temperature thing is actually telling you something. That's kind of interesting. So, suppose I have a case like this. This is kind of a typical situation. A plus B, C plus F.
Can you use a down curve marker?
Yeah, sure. Is that better?
Yeah.
All right. So at low temperatures, this guy comes in and mostly goes down to here. Maybe some of it goes across to here. Maybe a tiny bit goes across to there. Okay, so that's low temperatures at some medium pressure. When I increase the temperature, at some point, this guy, as soon as he's formed, he can kind of react over to form D, and D can react to form C, because this is the lowest barrier in the system. And so at some temperature, this interconversion of C to D is going to become really fast. And if your pressure is low enough and your temperature is high enough, you can be in a case where this interconversion of C converting to D and back to C and back to D can be faster than the rate of collisional energy transfers. Even faster than single collision, but certainly faster than the rate of thermalization of the whole energy distribution of B Boltzmann. And so in that limit, it doesn't make too much sense to talk about C and D as separate species. Certainly, they're interchanging faster than a single collision. It's like, from the point of view of bimolecular reactions, they're one species because they're always in equilibrium from the point of view of bimolecular reaction. By the time a bimolecular guy comes up to react, the two of these guys are always in a certain ratio. They're just basically set by the thermo, not set by anything about kinetics of this rate, because it's too fast. So in that case, it might be better to rename these guys Q. This is now species Q, and now I have a single well problem. A plus B goes to Q goes to E plus F. And then I can solve that one perfectly fine. So what Georgievsky's method does is analyze at high temperature, identify when this kind of problem is happening, and say, whoa, 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 your definitions of species are all wrong. You shouldn't have rate coefficients for C goes to D anymore because you're at such high temperature and such low pressure that those two are no longer separate species. From the point of view of bimolecular reactions, they always react as a single species in equilibrium. And therefore, let's call them Q instead. So he goes through your whole kinetic model, finds everywhere you have a C or a D, replaces it with a Q, appropriately adjusts all the rate coefficients and the thermo and everything to get a reasonable solution, and then goes back and recomputes the chemically significant eigenvalues thing using Q instead, treating this as if it's just one well. So this whole thing here is now just one species, and then it works fine. So that I think that this can overcome the high temperature problem, at least in most cases. However, to my knowledge, this is not really caught on yet, so maybe you guys would be the ones to start to do that. The challenge with it is that the reason why you had C and D was because you liked C and you liked D. You thought they were important species to you. And if somebody goes along and gets their computer goes and erases all your C's and D's and makes them all Q's, you get kind of annoyed because you cared about C and D being different species at some point. Otherwise, you would not have spent the time to write it down. You would not have spent the time to calculate the thermo for C and D separately. If you thought they were really one species Q, you would have called them Q from the beginning. Right? So there's like an intellectual thing here about what you're doing. And it also implies that kinetic models should be different at different temperatures. So you have a model that might be valid at 700 Kelvin. When you go to 1100 Kelvin, it might be completely wrong. That's also kind of weird. So wrong, it's not just the numbers are wrong, that the species are different. It's kind of a bizarre concept, actually. But I think it might be true. But anyway, so it hasn't caught on yet. Maybe it will. All right, some technical issues. RMG has to estimate the rate coefficients, the microcanonical rate coefficients as a function of energy. But you did not tell RMG what those are. All you told RMG was K of T. So RMG has to figure out what it thinks K of E is, because in the master equations, there's no temperature. Master equations are energy resolved, so they need K of E. K of E is not the same as K of T at all. The reason why K of T is Arrhenius is because it's a Boltzmann average of K of E. But if you get rid of the Boltzmann average, it's not Arrhenius anymore at all. So it's some weird K of E thing. And there's another quantity called rho of E, which is the number of energy states of the molecule that are very similar in energy. Because in the solution, it's going to lump energy states of the molecules that have approximately the same energy. It's going to lump them all together and say that there's just one state. It's not going to worry about the fact that there's 27 different vibrations that all have approximately the same energy. It's just say basically they all react about the same. Physically, that's fine, but it means you need to know what that number is, the rho of E. But we don't know that either, because all we told them know about the molecule is its thermo. We know it's NASA polynomial or something like that. And so the way it is done is the rho of E is estimated RMG from the estimates of the heat capacity, and also from, it looks at the molecule structure and tries to figure out what functional groups are there, and it knows some standard vibrational frequencies characteristic of different functional groups. And it combines that information to try to estimate what rho of E is. Then once it has rho of E, and if it also has K of T, the Arrhenius forms that you put in, with your rate rules, for example, then from these two, it can do a method called inverse Laplace transform to get K of E. Now, this is pretty rough. Inverse Laplace transform is not that perfect at giving you K of E's and rho of E's. And this thing with like the vibrational frequency estimates and stuff is a very Rube Goldberg kind of way to do this. So if you really do know, say, the vibrational frequencies of the transition state, you should use them. And you can, there's no way to put them into RMG right now, at least I don't think so. But there's definitely, you can put them into Arcane, or there's another competing program called Mesmer. And those programs can take all the details you know about the problem and put them in, and they'll give you much better estimates of rho of E and K of E than you would get from the RMG estimates. Now again, the RMG estimates have this great advantage that they're super fast. So you'll get an estimate of this thing in like milliseconds in RMG, whereas if you have to actually do quantum calculations to get the transition state vibrations, that might be a couple days of your time to get it. So there's a lot of reasons to do it the way RMG does, but it doesn't mean it's the most accurate thing in the world. Some problems with the inverse Laplace transform method that's used here. It relies on having the function of temperature for all the way from t equals 0 to t equals infinity. But we really don't usually have that. We usually know like rate coefficients in a range of normal temperatures, say room temperature to 2000 Kelvin or something. And outside that range, we can guess, but we really don't know what k of t really is. So when it's doing the inverse Laplace transform, it has problems. It has to figure out sort of what to use for what's the rate coefficient at absolute 0, for example, or what's the rate coefficient at 5,000 Kelvin. And these are, you certainly don't have them experimentally, and your estimates could be a little bit uncertain. And it turns out you're really sensitive to what you assume about absolute 0, the shape of the k of t curve, for example, as it goes to absolute 0. And so if you're a little bit off there, it actually makes a pretty significant difference in the k of e you infer. Also, the inverse Laplace transform method implicitly assumes that all the functions involved are smooth, but in reality, both k of e and especially rho of e are quantized quantities that are not really smooth functions physically. So what it's going to give you is a smoothed out version of k of e and rho of e, which looks something like the real one, but it's definitely not the same as the real one. And then there's some numerical issues about how to do this, and usually it works, but I wouldn't guarantee it would always work. So the PDEP implementation is not exactly the same in Cantor Arcane and in RMG. Basically, oops, let me finish this. RMG uses an extra class of functions that are just all about all these approximations and estimates and inverse Laplace transforms, all kinds of stuff that's RMG specific. And Arcane tries to be more intelligent, just use good stuff. But RMG has to be hooked in well to RMG with the quantities that's available at the time RMG is making the estimates. The master equation problem is based on solving equations like this at every energy level, but actually there's a continuum of possible energies, a very large number of different possible energies of the molecules, and so what we do is we discretize, and we draw little grains to break up, to discretize the energy. How you do that discretization affects the solution a little bit, particularly if it's very coarse. The finer you make that graininess, the more it will converge to the real solution. But it will cost you more time and more memory to do that. So in RMG, by default, it makes some estimates of what the energy grain should be. It has some like heuristic rules and what energy, how high energy you have to go before you're converged. But if you really care, you might want to fiddle these numbers and make sure that you get the same result. If this result you get depends on these numbers, then it's an indication you haven't really converged. Probably in RMG you would not do this. Maybe in Arcane you might do it, because then you really care about the answer. But if you see sometimes you have one reaction that do something really weird, this would be one thing you could try to see if this is the cause of the problem. And be aware that because you're discretizing, your thermo that you would compute from the discretized thing is not the same as the thermo you have originally. And also because we did the inverse Laplace transform, we did a whole lot of steps. Each of the steps was a little bit of error in, and as a consequence, at the end, the thermo was slightly different than it was originally. And again, if you really care, like about the equilibrium constant, your results might be slightly off and you're wondering why, this would be one of the reasons why it might be different. All right, that's all I had to talk about the pressure dependence. Any questions?